Hi, this is Vassilis Zikas, and I'm going to present the work on proof of reputation blockchain with Nakamoto Fallback, which is joint work with Len Kleinrock and Rafail Ostrovsky. So here is an outline of my talk. I will start with a very abstract discussion of what is a blockchain ledger and what is a blockchain ledger protocol. Then we'll discuss how we can use reputation as a resource. Then we focus on our construction of proof of reputation blockchain, and finally discuss how we address an inherent issue in reputation as a resource in our work by a backup proof of stake blockchain, or in general Nakamoto blockchain. So let me start with what is a blockchain-based ledger. So as the name suggests, a blockchain ledger is a ledger, so it's a system that stores a blockchain. This is a sequence of blocks that are connected by hash pointers, and it offers to its users the following functionality at a very abstract level. So the users have transactions that they can submit and they want to insert in a block. Those transactions are validated if they are found valid with respect to the current state of the ledger. They are added to a pending as next block. More transactions that come in are validated. If they're valid, they're added to the next pending block. Some transactions might be considered invalid. And what happens is that periodically the pending block is actually added to the blockchain. So this is one function of a blockchain ledger. The second function is that users can query the ledger for its contents. They can ask the ledger for its state, and when they do, they get as an output the state. And another user can also ask. And the very important property of the ledger is that when two different users ask the ledger, if the state of the ledger is the same, they learn the same thing. So they get consistent outputs. This is, again, a very idealized form of what a blockchain ledger is, but let's for now go with that one as an abstraction. Okay, so how does a protocol for implementing such a ledger look like? And again, at a very abstract level, I'm going to go in lower details in our protocol. We have a number of parties that are the protocol parties. Usually those are called miners, as a legacy name from Bitcoin, where parties mine by trying to hash. And what those parties do is they know the state of the blockchain, hopefully a consistent one, and they receive from the users the transactions. They pool them in local transaction pools, in sets of all valid transactions. And what happens is that periodically one of or more even of their users is chosen to be the one that proposes the next block. The chosen user puts all the transactions that he knows and are currently valid on a block, communicates the block to everyone along with evidence that he was actually chosen, and then everyone adds the block on the blockchain. This is at a very high level what happens. So to make this a little bit more concrete, the two key questions that we ask when we're designing a blockchain ledger protocol are who can propose the next block, and how can the miners agree on the blockchain ledger state. The first question is the one that mainly differentiates the different technologies that are used for implementing blockchain ledgers. The two most widely known are proof of work, in which the person that proposes the next block is chosen according to the hash power he invests in the system. The second one is proof of stake, where the person with the highest stake has highest chances of being chosen to be the next block proposer. And the one we consider here is proof of reputation, in which the chances to be the one that proposes the next block are proportional to one's reputation. Now, the second question of how to agree on the blockchain ledger state is pretty much uniform in all these settings. And it says that we are actually running an implicit consensus mechanism based on the assumption that's underlying the system, which is majority of honest work, majority of honest stake, or in our case, accuracy of the reputation estimate. And I will say what I mean by accuracy and quality, actually. This brings me to the second part of this talk, which is how can we use reputation as a resource for supporting the security of a blockchain ledger. The idea is that we will have what we call a reputation system. What is a reputation system? It assigns to each party, or let's say its reputation having party, a reputation that corresponds to the probability that this party behaves honestly in the protocol. This is the natural interpretation of more reputable parties have more chances of being honest. In the case of our analysis, we're going to assume uncorrelated reputation, namely the events of becoming corrupted are pretty much independent between different parties, which actually creates a very nice interpretation of the reputation. You can think of it as a rank of the sort that you have at Yelp or TripAdvisor or eBay. So it's a number corresponding to the probability of me being corrupted. It's independent of everyone else. We have in the full version of the paper a more general treatment as a general probability distribution, but this is a much harder case. Now, how can we use a reputation system? But the idea is the following. If I choose a subset of the parties, then by knowing the reputation, remember that's the probability of being honest, I can actually estimate what's the probability of having an honest majority in the set I chose. Or I can actually do something more useful. I can use the reputation of the different parties to actually select a set that has very high probability of having honest majority. And as we're going to see in a minute, honest majority is a property that we will want from any selection of parties that we do. So how do we use reputation in our construction to devise a blockchain? The protocol idea is actually very simple and elegant. The timeline is divided in block rounds, where each such block round might be several protocol rounds. And in each such round, a block is proposed and agreed upon. So what happens is that at the beginning of each such round, every party locally samples a very small polylog size committee, which we will call committee of endorsers. And inside this committee, it samples an even smaller, say constant size, 3 or 5, subcommittee of block proposers. And then the parties perform the following 3 steps to complete the block round. First, the proposers broadcast to everyone all the transactions that they have seen up to that round and are still valid. In a second step, the endorsers take the union of all transactions that they've heard being broadcasted. Since they're broadcasted, again, this is importantly, the broadcast is a Byzantine broadcast, so it's consistent for everyone. So they take the union, which is the same for everyone. Each of them signs it and sends the set and the signature to the other parties, only to the other endorsers. And finally, endorsers collect all the signatures that they see on the set that they know, and if they see a set which has support of a majority, they diffuse it to everyone. So what's important to notice here is that the first 2 steps only involve communication among CBA, which remember is a small subset of the entire player set. And only in the 3rd step, we have a diffusion of the message sent through a network which we don't really know. So this means that we don't need to flood. We don't need to go and send to other parties, other neighbors send to other neighbors and so on. We can directly communicate, which really limits, it reduces the communication overhead of the protocol. So to give you a graphical animation, if you want, of how the protocol proceeds, in every round, we select, as we said, a set of endorsers. And in this set, a subset of proposers. And let me focus on that one. What happens in its block round is the proposers take all the transactions that they know, and each of them broadcasts it using a Byzantine broadcast protocol. This means that every party hears exactly the same thing. What do they do then? Each party signs the set that he heard and sends it to everyone else in this set. So once this happens, we zoom out, and every party that sees a majority of signatures on this set propagates it to the network, and now it diffuses by a standard diffusion methodology, as it happens with most cryptocurrencies, but only in one step. And whoever sees such a set which has a majority support from the actual block round endorsers committee accepts this as the next block. And then we can go in the next block round, select another endorsers committee, another proposers committee, and so on and so forth. Now, what are the assumptions that we need for this protocol to work? On the network side, we actually assume synchrony. This is in the paper. We can actually remove synchrony and replace it with partial synchrony, which is pretty standard, but this analysis is not there. And we also assume the common knowledge of the genesis block as usually, which includes the keys of the reputation parties and the reputation system that describes the reputation of each party, so that we do the lottery in the way I'm going to describe in the next slides. So what do we need for the protocol I described to achieve its goal and be secure? We need to make sure that the committee of endorsers that we are selecting has a majority of honest parties. And this majority will ensure that if anyone accepts a block, then this block can be unique. There cannot be two blocks supported by the majority if the majority is honest. And secondly, we can actually, in the round where the block proposers propose their broadcast their transactions, they can actually use an expected constant round broadcast protocol, which will reduce the time of the overall protocol. So honest majority is a very important property we want to achieve. So the question is, how can we sample the committee so that it has honest majority? All right. So what are we trying to do? We have a set of parties where each party has a reputation. This is the probability of the party being honest. And we're trying to select a small sublinear and then another one small constant size committee, where in the sublinear committee of endorsers, we have honest majority. Now, can we do that? Not always. If the reputations of the parties are bad, right? So if the parties are not reputable, we cannot do it. Of course, if everyone has a high probability of being corrupted, there is no way we can select any committee of honest majority. That's a very simple thing to verify. However, for any reputation system which would allow such a selection, we know of an algorithm that allows us to actually sample an honest majority set. So if there is a way to sample an honest majority set of polylog size, then there is an algorithm by Asarov, Lindell, and Zarosim that tells us how to do it. And the way to do it is very simple. What we do is we sort the parties in decreasing reputation, and then we select sufficiently many from the most reputable to the least reputable. If the reputation system allows for honest majority committees of the size that we are looking, then this will give us an honest majority, because it always selects the parties with the highest reputation. Now, as a side note, I will refer to reputation systems which do allow for honest majority committee selection of the size that we want as feasible reputation systems. What this theorem says is that feasible reputation systems always allow us to select honest majority with this algorithm. So are we done? Unfortunately not, because this algorithm has an issue with fairness. So it is the case that always the parties with highest reputation are selected. So even if a party has very good reputation, but it's not among the highest, he will never be selected in the protocol. And that creates an issue with participation, right? Parties with low reputation don't even want to be part of this protocol because they don't even care. So what we introduce is a property which we call reputation fairness, which has the following desideratum. First, we want that the higher the reputation of a party, the better the chances that this party is selected in the endorsers committee. Second, we want that parties with about the same reputation have about the same chance of being selected. And third, we want that the representation of parties from different reputation levels to the final set is proportional to their actual reputation. So you might be wondering why I'm introducing 3. Might look that 3 is implied by 1, but this is not the case. Think of the following example. Assume that I have a reputation system with M1 parties that have reputation 3/4 and then M2, 4 times M1 parties that have much lower reputation, 1/4. And now I go and select each party to be part of the committee that I want with probability exactly proportional to its reputation. This means that I'm expecting roughly 3/4 M1 parties to be from the set that has reputation 3/4. But then I'm expecting roughly another M1 to be from the set that have reputation 1/4. And that's really bad, right? Because I'm selecting way too many parties with reputation 1/4. So if you do the math, you're going to see that in the final set, although I have a lot of parties with a very high reputation 3/4, I'm not even succeeding in getting a honest majority committee. What do we do instead? We introduced a tiered approach to reputation fairness. So we divide the parties into tiers according to the reputation. Here in this demonstration, I have 4 tiers, parties with reputation higher than 3/4, parties with reputation half up to 3/4, parties with reputation 1/4 up to half, and parties with reputation less than 1/4. And note that with what I'm going to do now, we're going to actually have inclusivity by our fairness notion, even to the low reputation parties, but with lower representation, of course. So now, the way that the reputation fairness desideratum is translated to this tiered reputation setting is that a party from the reputation tier TI, the ith reputation tier, is twice as likely being chosen in the committee as a party from the immediately lower reputation. By the way, depending on the number of tiers, we can play with this parameter to be something definitely bigger than 1, but have like a different level of representation. We can do a different level of probability depending on what we want here. Second, parties from the same tier have exactly the same probability of being chosen in the set. And third, the number of parties from the higher tier TI is twice the number of parties from the lower tier. And once again, we can play with this twice and make it C times. And if you look at what this gives us, at least with the twice as high, if we have more than, say, 4 reputation tiers, this will always guarantee honest majority in the committee. This property will always guarantee honest majority in the committee. Of course, with overwhelming probability, with very high probability, just by having sufficiently many parties in each of the high reputation tiers. So if there aren't sufficiently many, there is a way to counter. I'm not going to discuss it here. So how do we sample to achieve the guarantees from the previous slide? Where our algorithm does the following. It selects a number L1 from the highest reputation tier, then another number L2 from the highest together with the second highest, their union. And if I select the same guy from T1 twice, then I just replace him and get another one. Then another number L3 from the union of the first three reputations, and so on and so forth. And L1, L2, and L3 are computed so that they satisfy certain conditions. I'm not going to go into details, but by doing some not too complicated algebra, you can see that those beautiful equations give you exactly what you need, that the number of all parties you're choosing is polylog, log to the 1 plus epsilon, and all the properties that we wanted from the reputation fairness definition. It's easy to see that the previous algorithm will give us the guarantees that we need, but I want to highlight that because of using reputation, we also get some very nice properties that reputation has. First of all, we get finality, which is common in iterated PFT blockchain. So the next block is decided and agreed upon the end of the block round. More importantly, the reputation can be thought of as information that is given to us about the adversary. And this, for example, means that we don't need to worry about the adaptive corruptions, right? A party with high reputation will not get corrupted with the probability that his reputation indicates. So this means that we don't need to have the lottery itself private. We just need to worry about the randomness, is what we do here. And perhaps even more importantly, we can actually have parties communicate with each other over direct channels. They can know each other because they're parties with reputation and they are bad. Their network is also bad and attackable with this reputation. So this means less flooding, as we saw, which means less communication over it. However, it does come at a cost. And one would argue that reputation is a subjective resource and manipulatable. So how do we deduce reputation? We observe a party's behavior, we get information about what he does online and so on, or what he does in our protocol. Now, a party might behave honestly until he gets high reputation and then attack the system. This means that our reputation system might not reflect exactly the probability of it. So how can we address that? We address it by devising a hybrid design that uses proof of reputation as a primary blockchain. So it harvests all the nice properties from reputation, but to make sure that our reputation estimate doesn't create security issues, it also operates in parallel a secondary Nakamoto style blockchain that's based on a different assumption. For example, proof of stake. Importantly, on the secondary blockchain, we only post digests from the primary blockchain, no transactions or nothing. So this is a very lightweight use of the secondary blockchain. And what we prove for this combination, I'm not going to go into details, but I will just tell you what the result is here, is that if the reputation system is accurate, then we don't even need to worry about the secondary blockchain. We enjoy all the nice properties. But if we have a bad estimation of the reputations, and it happens that we assume that a party might stay honest with high probability, then it actually might. Then, if the fallback security guarantee is true, right? If the if the majority of stake is actually in honest hands, if you want proof of stake, then still our system remains secure. Might not be as efficient, but it remains secure, and we can use a secondary blockchain to bootstrap and go back to the primary blockchain and enjoy all the nice properties. So in some sense, we can have the pie and eat it too. To conclude, in this work, we discussed how reputation can be used as a resource for efficient blockchains. We devised the definition of reputation fairness, which boosts inclusivity in a blockchain protocol, and therefore incentivizes potential participation. And we showed how to address the subjective nature of reputation by a Nakamoto fallback blockchain, which gives us security even if we have a bad estimation of the reputation. There is numerous open problems here. The first one is how can we actually estimate reputations properly? This is related to an AI. How can we use information we have about the different reputation parties to assign to them reputation accurately, which is also important for the bootstrapping of any system relying on reputation. The second one is how can we have incentives that make parties want to increase their reputation, right? So reputation is something abstract, but it can be connected with real properties, but we want like an analysis which shows that parties do want to increase reputation and how we can use reputation potentially to penalize parties that misbehave. And the third one is that our analysis currently is asymptotic. For a more practical system here, it would be good to have a concrete analysis with concrete parameters and error probabilities. This is also something we are planning to work on, and happy to hear input. So with that, I would like to thank you.